Okay, a couple of announcements before we get started. Your exam 2B, which is primarily on NMR, opens today at 12:15 and closes tomorrow. That's in zip grade. Your interim grades, letter grades have been posted in SOAR, and your module exam points have been updated in Canvas, and your rank and Z-score are also posted in Canvas. So rank is just where you sit out of your cohort, and the Z-score is based on how many points you have relative to the average and the standard deviation. So 0 is essentially average, and anything that's positive means you're performing better than the cohort. Anything that's negative means that you're performing below the average. So I give those numbers to you just so that you're aware of the effort that you're putting into the class. So those are strictly numbers based on the points you've accumulated. So that has nothing to do with your letter grade that's reported, but it gives you an indication of your performance that you're putting into the class and where you stand. Any questions before we get started? So we were talking about proton NMR and these reasons why the signals look different. So the location on the x-axis was the chemical shift. That's the Greek letter delta reported in parts per million. Then we talked about why the signals split due to the n+1 rule. And then we talked about the intensity of those signals having to do with the spin of the nucleus. And so today what we're going to talk about is the distance between the lines in the signal. So essentially when two things couple to one another and the signals split, then you get this distance between those lines. And we're going to talk about what that distance is and the physical property that it's related to. So we're going to need the model for that. And this is a good segue into Module 3 when we start talking about physical properties of these molecules. So to preface the discussion here, we're going to continue on with our molecule here, 2-butanone. And so just ask some simple questions here. What are the hybridization of atoms in the C3 to C4 bond? And so they're listed in that order. This is carbon 3, that's carbon 4. So when we look at them, we see that we have only sigma bonds indicated. And so we know that carbon 3 is a CH2 group and carbon 4 is a CH3 group. So these would both have to be sp3 hybridized carbons. So if we do the same thing for carbon 2 and 3, we see now that carbon 2 is showing 3 sigma bonds plus 1 pi bond. So that has to be sp2. From the prior problem, we figured out carbon 3 was sp3. So our answer here is B, sp2, sp3. And it says, what is the type of bond between carbons 3 and 4? So we see that it's just a single line. So that has to be a sigma bond. So that's A. So carbons 2 to 3, that's sigma. 3 to 4, that's sigma as well. So which of the following statements is true? So we know that to form a sigma bond, we have overlap of two sp3 type orbitals. And so the consequence of that is the sigma bond has free rotation. Notice this carbon-oxygen pi bond. When two atoms come together, they overlap with p orbitals. And so the p orbital, remember, you have a cloud of electrons on top and bottom. It sort of looks like a hamburger bun. What that does is it locks the rotation so that the sigma bond can no longer freely rotate. So understanding that is going to be crucial to understanding why the magnitude changes between the lines of a proton NMR signal. So as I said, we use the n+1 rule to predict what a signal would look like, and that's you're just counting all of the neighbors and adding 1. The 1 comes from the spin states for proton can be +1/2 or -1/2. So when signals split, we go through those approximations. You have a little bit that moves upfield, that's towards 0, and a little bit that moves downfield, that's away from 0. So after you determine the unique number of sets, say you had one neighbor that splits into a doublet, you get a little bit going this way, a little bit going the other way. So that's upfield and downfield. And now you have that distance between them, and that's what we're gonna measure. That magnitude is reported in hertz. And really what we want to figure out from that 2-butanone, when the CH2 group and the CH3 group couple together, does that coupling lead to the same magnitude for the triplet and the quartet? Any questions? So here was the spectrum. Of our 2-butanone. We said that the quartet belongs to the CH2 group, the singlet belongs to the CH3 group at carbon 1, and then the triplet belongs to the CH3 group at carbon 4. So again, notice the singlet, there's no neighbors, so it's just a single peak. The quartet, as shown in this red number down here. So I'm highlighting that in yellow. That number is the integration or the ratio from the uniqueness. So it integrates to 2. There's 3 neighbors. We add 1, so we get the quartet. The triplet, that integrates to 3. There's 2 neighbors, so 2 + 1 is 3, so it's a triplet. Now, what we're concerned about for the quartet, we have 4 numbers. So let me highlight those in yellow. So I'm highlighting these numbers at the top. And basically, those are the chemical shifts for the 4 lines in the quartet. So what you'll notice now is of the 4 lines, we can calculate 3 differences. So differences or distances. So I'll just call this 1, 2, and 3. So whatever number of lines you have, you just subtract 1, and basically that gives you the distances between those signals. So that distance, you can sort of eyeball it right now and approximate that those three distances are all equal, right? So a couple of things, that's not always the case. And so we want to understand why that is. And then what is the magnitude of that distance? So this is called the coupling constant. And it's signified as J, and it's reported in hertz. So what we're going to do on the next slide here is just look at each number and then subtract the lower one. So 2.4868 minus 2.4685, and then we do that for the other two distances. And so in the table, I'm showing the 4 lines. So there they are. And then for each line is the chemical shift. So that's reported in parts per million. And then we're basically taking 2.4868 and then minus the next line. So minus 2.4685, and that gets us the difference. And notice that the unit is parts per million. So we have to multiply that by the instrument operating frequency. In this case, it was 400 megahertz. So this number times 400, that converts the unit to hertz. And so we end up with 7.32. And then you can do that for the remaining cases. And what you'll see is that you're all basically arriving at the same number, so 7.3. So it's called a coupling constant because no matter what field strength of instrument you run it on, you're always going to get the same value. So if you ran this spectrum at 600 megahertz, basically the difference in the ppm would change. Then you multiply it by 600 and you're still going to get 7.3. So remember that for any 1 ppm unit on this instrument, that is 400 hertz. So if you were operating at a 600 megahertz instrument, 1 ppm difference would be 600 hertz. So for the quartet, we got 7.3. And so now we're going to look at the triplet and see if we get the same value. Because those neighboring protons influence one another, basically we should get the same value. The coupling between them should be the same magnitude. So we have the triplet. There's the chemical shifts of the 3 lines highlighted in yellow. So we have 3 lines, and so we have 3 minus 1, that's 2 distances. And basically what we're figuring out, are those distances the same? We set up the same table. Here's our lines, the 3 lines. There were the chemical shifts. We take 1.0756 minus 1.0573. That gets us the distance difference in ppm. We multiply by 400, And now look, 7.3, 7.3. So that tells us the distance between the lines in the triplet, but also that confirms that it's coupled to the quartet. So there has to be a reciprocal relationship between coupling. So coupling constant, the constant means a couple things. Again, regardless of whatever instrument frequency you're on, it's that for that compound, that's always going to be 7.3. Constant also means the distance between those lines. So notice we came out of this one with two approximately equal values. So I'm saying that's true for this case, but that's not necessarily true in general for everything, as we'll see a little bit later in the lecture. So the questions, so what if there is not free rotation about neighboring hydrogen groups? And then what factors influence the magnitude of the coupling constant? The coupling constant can change. And so for proton, you can generally get between, at the low end, about 1 hertz to the high end, about 15 hertz. And so what changes that? What is responsible for that? Any questions? So to understand how the coupling constant changes, we have to think a little bit more in 3 dimensions, and that's where the model is going to help us. So I think you all have this type of model kit for your lab. This is the same thing, it's just the bigger instructor version of it. So we have carbon here at the vertex, 1, 2, 3, 4 bonds, so that's sp3 hybridized. So what I'm showing is basically 2 sp3 hybridized carbons. I'm going to call the yellow balls hydrogens, and the red and the blue are just other groups. They can be hydrogen, but they're to show you how things change so that everything's just not yellow. So to understand the magnitude of the coupling constant, we need to introduce this concept called dihedral angles. So normally when you think of an angle, you have 3 points, and then you're measuring, the angle between the 2 lines. A dihedral angle is a little bit different. So it consists of basically 2 planes, and then you're measuring you're measuring the angle between the planes. So if we look at our 2 butanone here, and so this is the way I'm normally drawing it, right? And we call that a zigzag. So the zigzag comes from putting the carbon chain in one plane. But we know that since we have these sp3 hybridized carbons with hydrogens attached to them, they can't be in that same plane because the carbon is tetrahedral. So things have to sprout out either towards you or away from you. So let me highlight in red here these bonds, just the regular looking bonds. So those are all in the plane. And then when we go back and fill in the implicit hydrogens, we see that some of them have to come out towards you. And so I'll highlight that in blue. That's a bolded wedge. So anything that's darkened is coming out towards you. And then in green, I'll use the dash. That's going away from you. So really that's how we need to start thinking about these molecules so that we can understand not only this concept, but when we start learning about reactions, where on the carbon chain a reaction will take place. The three-dimensional picture or concept is important to us because we have to start talking about trajectories. So to summarize that real quick, so say you have these 3 points, and then that would be the angle between them. So those 3 points also make up a plane. But now imagine you have another 3 points in a separate plane. So what we're going to look at is the angle between the planes. That's the dihedral angle. So that we're all on the same page here, let's just classify how many hydrogens are in the plane, how many are towards you, and how many are away from you. So we'll do the reds. We'll do the reds in the plane. And again, that's just using the regular line. So there's 1, 2. We'll do the blues towards you. So 1, 2, 3. And then the greens away from you. 1, 2, 3. And from that, I believe we end up with B. So here's our structure again. And let me just color. I want to color one of these red. So I'll say HA is red, and then HB is blue, just so that I can match onto that model there. So we want to figure out what is the angle between HA. So that was the red one, and HB, the blue one. So what you see, just from that line notation, HA, C, and C, that's one plane. C, C, and HB, that's the second plane. So the dihedral angle is the angle between those two planes. So the learning tool that we're going to use to do that is called a Newman projection. And the way that we do that, say for example, say that the red and the blue are just other carbon substituents, and I'm holding them in the plane in a zigzag. That's the way you're normally used to looking at things. So you have these 2 hydrogens right here, 1 and 2, they're pointed out. 3 and 4, they're pointed back. So wedges and then dashes. So what the Newman projection does, instead of looking at the zigzag perpendicular, all we're doing is rotating it. So I'm going to take it and just rotate it towards your eye. So when we do that, we see 1, 2, 3 bonds. And so that's notified or drawn there as the front carbon. So where they meet in the middle there, that's a carbon. And then you have the 3 substituents sprouting off. Or you can draw it the other way where you have a bond going down like that. So either way. Now the rear carbon is shown by the circle. So I'm coloring that in red. So you have this front carbon, you can see the substituents. Now the circle is the back carbon in my left hand. And then sprouting off from that are its 3 substituents. Notice you don't see the full lines. You just see that little baby bit of line coming off the circle. That's the back carbon. And then what you do is you just stick the front carbon in front of the back carbon, and then you get the Newman projection shown here. So overall, you're seeing the 6 substituents. But what you have to realize from this learning tool, you are now looking down a bond axis. So in my right hand is a carbon, my left is a carbon. You're looking down that axis. So that means there are 2 carbons there. And then the other one, we're just moving the substituents around, because remember we figured sp3, sp3, and then that's a sigma bond. So there's free rotation. So let me do some coloring here. So we said that was red, and this was blue. So in the nomenclature here, it says, let's do this for C3 to C4. So this means front, and that means back. So 1, 2, 3, 4. So for the problem on the left, really what we're doing, because the backbone is in the plane, we have to put our eyeball in that same plane. And so we want to put our eyeball right here. And we want to look down the 3 to 4 bond. And then from the Newman projection, just stick in all the substituents. So let's see if we can sort of do this in our head without the model first. So if your eyeball's in that plane in carbon 3, so that's the front, carbon 4 is the back. On carbon 3, the front carbon, what should I write at this top substituent? So maybe let me do it. Make sure I get my performance here correct. So if this is HB, and this is the other H, so HB is towards you here, HA. If we want to look down 3 to 4, what I'm going to do is rotate this way. So see where HB ends up, and then this H, and my dome is the carbonyl group. So you can do it sort of 2 ways. like in your mind, if you can envision being in the plane looking down that bond, or if you can, in your mind, rotate the zigzag. That HB on the chain, because it's down, it has to remain down. It's coming out towards you, and then really, if however you're rotating, you're rotating in your mind, it's got to be to the right, and then that other hydrogen to the left. So it's about, in physics and math, they talk about viewpoint and frame of reference. You're changing your frame of reference. So we're going to say this is HB, that's H. And then as we look down that bond axis, 3 to 4, the carbonyl group and then the methyl group at 1 have to be up. So based on that, we'll do the back substituents. HA should go where? So left, right, or bottom? Huh? It has to go right. So notice, because HA and HB are both wedges, they're coming out towards you. On the Newman projection, they have to remain on the same side. And then the other things are the same. They're both hydrogens, so H and H. So what if we're doing the other way? And so we want carbon 4 in front and then carbon 3 behind. So that means our eyeball is right here, looking down it that way. So what I can tell you is so there's our zigzag in yellow. When you're looking down that carbon 4, you see how the hydrogen that's in the plane is pointing down? So that has to point down in the Newman projection. And then HA should go where? Left or right? So it should go left. And we know now that because A and B are on the same side, HB should go here. On the bottom right, that should be an H. And then what's going up is that carbonyl and then methyl group at C1. So again, at this point in the semester, there's going to be a bit of an incline in the learning curve because now we're talking about more visual things. Really what you're doing is you have a molecule and you're changing your viewpoint. whether you're looking at it 90 degrees or you're rotating your eyeball into the plane and looking down a bond axis. So your model kits will definitely help you with this, picking up that skill. We're going to use them quite extensively in Module 3, where we talk more about this, but we're also going to introduce a new form of isomerism called stereoisomers. And so that's something that students tend to find difficult in understanding as well, because at that point we're employing a lot of symmetry elements. And so if you have a tough time visualizing that in your mind, the models will help you. So looking down 3 to 4, I think for this one we said A was the correct response. So again, figuring out, what's in the plane, knowing from the zigzag what's going to go up, down, left, or right, can help you move from the sort of flat carbon chain to the Newman. And again, the Newman is important for a lot of reasons, but also it's used in another projection called a Fisher projection. And then as you learn more organic, they're used in different reference frames, and all of these models have different names. So 4 to 3, we wanted HA up into the left, HB down and to the left, so C is the correct response here. So one thing I might point out that can help you a little bit, I wouldn't say to necessarily memorize this, but sort of a learning concept. So there's the zigzag chain. And I want to focus on carbons 2 and 3. So maybe I'll say in that chain, carbons 2 and 4 are up. 3 and 5 are down. So when you sprout off substituents to it, on carbons 2 and 4, the substituents have to point up. So we would draw them in as a wedge and a dash. 3 and 5, they have to point down. So that's important because you don't want to get into the habit of for a carbon that's pointing up, drawing substituents that look like that, or something that's pointing down where the substituents are pointed the other way, because now you're not really visualizing it according to the tetrahedral geometry. So on the chain, carbons that are up, substituents are up. Carbons that are down, substituents are down. And then whether they're up or down, you have something pointing towards you and something away from you. Any questions? So now that we have an understanding of, taking a zigzag into a Newman, how can we use the Newman projection to figure out that dihedral angle? And again, we were concerned with the angle between the intersection of those two planes forming HACCHB. And the way we can think about it is if we take a circle and then we divide that circle by the three substituents. So we can think of this as our front carbon. Then we have the three substituents. And so all of these angles there are 120 degrees. So 360 divided by 3, that's 120. And then what we're doing here, so that would be a back carbon substituent. We're just bisecting that angle. So 120 divided by 2 is 60. So if we take the three substituents, we just make a circle. So 1, 2, 3. We divide that 360 by 3, that's 120. And then, if we're looking at, this angle H, carbon H, that was 120. Now if we look at this blue hydrogen on the back, down the Newman projection, that's bisecting that 120. So the dihedral angle from this hydrogen to this hydrogen, so H, C, C, H, that's 60 degrees. So the reason that angle is important is because it directly influences the coupling constant, the distance between the lines in the signal. And so this is known as the Karplus equation. So Karplus want to know about prize in chemistry for this work and other work in applying mathematical models to organic molecules. So the Karplus equation is shown there. Really what you need to be able to do is look at the graph and interpret the graph. So on the x-axis, you have your dihedral angles running from 0 to 180. And then on the y-axis, that's your coupling in hertz. Notice it's written as 3JHH. So what does the 3 mean? The 3 just means the number of bonds. So 1, 2, 3. The H and the H are just the two elements that are coupling. And so we said from the butanone, based on the Newman projection, there was our angle 60 degrees. If we run over now to the y-axis, it should be 4 hertz, but from our prior calculations, we calculated it as 7.3. So why is there such a huge difference? The other thing you'll notice when you're starting at a dihedral angle of 0, the coupling is 13. As the angle increases to 90, that's when it gets about its lowest to about 1.52 hertz. Then as the angle increases again to 180, it goes back up to about 15 hertz. So let's try to understand that. If we're just looking at now the red and the blue, this right here, what is the dihedral angle between them? Just these two right here. It's 0. So you have HCC, CCH. So those two planes, the angle between them is 0. Then I'm just going to do this. Now imagine they're planes that are moving. What's the angle between the red and the blue now? 180. So those are the two maximum, right? 0 degrees, 180 degrees. So everywhere in between there, you're just moving along that curve. The weird thing is, now notice when you get to 90, that's the lowest. Then it starts increasing again. So we won't talk too much now about why that is, other than that's the relationship. Really what it has to do with how that electron spin information is transferred through the bonds that are used. But you just need to understand how to interpret this graph. So you draw the molecule, you're given some sort of relationship, you make the model figure out what the angle is, then from the angle go to the graph, run over to the y-axis, and that's your coupling. So the reason that experimentally you do not see 4 hertz, so if we said if it's sitting like that, the angle was 60, so it should be 4 hertz. But what happens is, remember you have this sigma bond, and it's constantly rotating. So there's always this energy at room temperature. It's rotating like billions of times per second. So if you just focus on red and blue, it's not locked. So let me hold it like that. It's constantly moving between that 0 and 180. So overall, all of those angles average out to the 7.3 hertz. So sigma bonds have free rotation. And because of that, you're getting the higher than normal coupling. And so what is meant by that 7.3 hertz is that distance. So we calculated those distances to be the same. We just report it as one number, 7.3 hertz. So now the question is, what if you do not have free rotation? What if there's a situation where that bond can't rotate and the dihedral angle is fixed? How do you figure that out? The case example that we'll use is this molecule shown here, 3,3-dimethyl-1-butene. So there's the numbering. So we have a 4-carbon chain. Starting at carbon 1 is the alkene. Then on carbon 2, there's 2 methyl groups. So if we were to determine the uniqueness set of this, to a first approximation, you would say there's 1, 2, 3, 4 unique carbons. Then you could say, well, carbons 1, 2, and 3 would make 3 unique sets. So carbon 1 has 2 hydrogens. Carbon 2 has 1 hydrogen. Carbon 3 has these 3 methyl groups. So those methyl groups would make their own set. Then we would do the normal thing, finding the ratio, 9, 2, and 1. But what's weird about this case is here you have a pi bond. Remember that the p orbitals overlap so that you no longer get free rotation. So initially, while you might think that the hydrogens A and B on carbon 1 are the same, they actually end up being different because that bond does not rotate. So they're different in relation to the neighbor on carbon 2. So how many neighbors does HC have? So if we're just counting the neighbors, we see that that neighbor has no hydrogens. This neighbor has 2, or that neighboring carbon has 2 hydrogens. So a first approximation, you'd say, well, that's 2. 2 plus 1 is a triplet. So that's fine for a first approximation. But now again, the issue is that bond does not rotate. So to the first approximation, we said 2 neighbors. So 2 plus 1 equals 3. Triplet. So if you consider HC and HA, so C and A, what is the dihedral angle between HA or HC, carbon-carbon HA? It's 0. So the pi bond necessarily makes those hydrogens in the same plane. The fact that they're both on the same side of the alkene means that the dihedral angle is 0. CB, so HC, carbon, carbon, HB. What is that dihedral angle? 180. So now hopefully you can see where we're going with this. Even though the hydrogens on carbon 1, they're both attached to that carbon, their relationship to HC is now different because there's not free rotation. So therefore, when we look at the coupling, it cannot be a triplet. Because we saw from the Karplus curve something with a dihedral angle of 0 is going to have 13 hertz. Something with 180 is 15 hertz. So C to A that was 0. Then C to B was 180. So because that angle is different, the couplings are now going to be different. So what do we do? How do we basically figure out how is that signal going to look? So C to A was 0. So there's 0. We just run straight up the y-axis. And then we hit the point where it intercepts. And so that's 13 hertz. So C to A is showing a coupling of 13 hertz. C to B was 180. So we find that on the curve. We draw our line over, and we see that that is 15 hertz. So you can't have a triplet that's showing both 13 and 15. Remember, the distance between those lines has to be the same. So how do we figure this out then? Really what you have to do is you consider each neighbor as its own thing. So HA is a separate neighbor, it's 1. We apply the n+1 rule. 1 plus 1 is 2, that's a doublet. So that's going to be reported as a doublet. HB is its own unique neighbor, so that's 1. 1 plus 1 is 2. This is also a doublet. So that means HC is reported as a doublet of doublets, or DD. One doublet is 15 hertz, the other doublet is 13 hertz. And so this does make sense in the fact that a triplet really is a doublet of doublets where the distances between the lines are the same. And that makes the center line that 1 to 2 to 1 ratio. So what does it look like? We're saying from a first approximation, when we determine uniqueness, that HC is its own thing. So it's a single line. Then it has this larger coupling, so 3-bond coupling, C to B, that's 15 hertz. That splits into a doublet. So there's your 2 lines for the doublet. And they're spread apart by 15 hertz. Now you have this smaller coupling due to HA, and that was 13 hertz. So each of those lines then gets separated by 13 hertz. So 13 and 13. And so this is now reported as a doublet of doublets. So there's one doublet, there's the second doublet. see these two center peaks here? Notice the intensity, just drawing a horizontal line across, it's 1 to 1 to 1 to 1. If these couplings here, 15 and 13, were the same, these center lines would merge together, and then you would have the intensity 1 to 2 to 1 of a normal triplet. So really you can, if you imagine a triplet and you're just basically pulling it apart, that's making the doublet of doublets. And again, the reason that it's important to understand that is, as we move forward in the class, we're going to look at molecules where you do not have free rotation. Things are conformationally locked, so the angles between neighbors are going to be different. In Module 3, we'll talk about ring systems. When something is a ring, you no longer have that free rotation about things, and you lock these angles into place. So if we said, looking at HC, that's making A and B both different, right, due to the dihedral angle, but they're bonded to the same carbon. So this question is asking you now not what the dihedral angle is, but what is this angle? HA, C, HB. We have an sp2 hybridized carbon. So it's trigonal planar, so the angle between them has to be 120. Even though they're bonded to the same carbon, they're different, and they're going to couple to one another. So that would be a 2-bond coupling. So 2J, HA, HB. And so what would that coupling be? We just run over to 120. We draw our line up. Then we draw the line over. And we see that those two would couple each other with about a 4 Hertz coupling. Questions? Okay, so I figure what we would end on is another one of these problems. We got about 10 minutes. Let's go through and practice. Again, at this point, we're given all this data. What can we extract from each piece of instrumental information? How can we start making fragments, piecing them together to come up with a structural claim? So we have IR. So IR, mass spec, carbon NMR, and proton NMR. So the IR is showing what? We have this signal here at 2249. What functional groups could that belong to? So an alkyne, or what other functional group? Nitrile. So IR. So within that region, 22 to 2400, that's your triple bonds. So carbon-carbon or carbon-nitrogen. So we're off to, we got something. when we look at the mass spec, we see the parent ion M+, then we see these two numbers. I know it's teeny tiny, but if you look at the lines of those two numbers, what is the number telling you and what is the lines telling you? So we have 147/149. What'd you say? A little louder.
It's an M+2.
So it's an M+2, that's important. And then if you zoom your eyeball in on the intensity of those lines, does that tell you anything? What? They're even? Well, what does the 147 tell you? There is a nitrogen because it's odd. Then you have M and M+2. Those lines are even, so there's another heteroatom. Bromine. So odd equals nitrogen. M+2 line is equal height. That equals bromine. So at this point, what we could say is, going back to the IR data where we have this choice, alkyne or nitrile. The mass spec is saying there's a nitrogen. So at this point, we'll just move forward and say that the triple bond is a nitrile, because then that includes the nitrogen. And then we also have this other fragment, bromine. If we go over to the carbon NMR now, and so we're going to look at the bottom one that says proton decoupled. That's the normal carbon. We ignore the solvent. How many total lines do you see in that carbon NMR? 4? So that tells you there's 4 unique carbons. You have 3 of them clustered together, and then you have this one over here. We already have a carbon, right, from the nitrile, so that has to be your sp hybridized carbon. Then we have this cluster of 3. We look above to the depth. And remember, the depth is telling you how many attached hydrogens there are based on phasing. Positively phased signals are on top. Negatively phased are on bottom. So if they're on top, they have an odd number of hydrogens attached, 1 or 3. If they're on bottom, they're even, so 2. So you have 3 negatively phased signals. That's telling you they're all CH2 groups. And at this point, we have 5 fragments. We have a nitrile, a bromide, methylene, methylene, methylene. So there's really only one way that you can connect these. You have to put the nitrile at one end, the bromine on the other, and then the CH2s all linked together in the middle. So let's do that, and then we'll look at the proton NMR just to verify how the signals look. So we have N triple bond C, CH2, 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 and then bromine. So if we look at the proton NMR, how many unique sets do you see? So we see 3 unique sets. So that's just looking at the signals themselves. And then you see this line right here. That's called the integration curve. If you measure the distance from top to bottom, like in millimeters, you get some value, but if you look at all of them, they're all the same height, right? And so essentially what that's telling you is the ratio between them is all the same. And we can already confirm from the carbon NMR that each of them has 2 attached hydrogens. So 2, 2, and 2. So that's our uniqueness set. So 3 unique sets in a ratio of 2 to 2 to 2. Just as a review, in blue, let me number these carbons 1, 2, 3, and 4. So we have this right here, this triplet at about 3.5. That triplet would belong to the hydrogens on what carbon atom? Carbon 4. So that carbon has a bromine attached to it. That's an electronegative heteroatom, so it's going to shift it the most. We see it's a triplet because we look over it as 2 neighbors. Then we see this other triplet at about, is that 2.6? So that has to be the carbon or the hydrogens on carbon 2, because it's also a triplet. The hydrogens on carbon 3, you have 4 neighbors, so 4 plus 1 is 5. You can assign it to that signal there just based on the number of lines in it. So altogether, that fits nicely in explaining everything that we see based on that structure. So again, when you're teasing this data out, once you get started, then the snowball starts kind of rolling, right? Because then you can confirm things with the number of carbon atoms, the attached hydrogens through that depth spectrum, and then you can go back to the proton and make sure that you're not violating any of the ratios or the Lewis dot rules at all. Any questions before we wrap up here? All right, so your exam 2B is going to open in about a minute. You'll have 24 hours to do that on ZipGrade. There's 30 questions and then 9 bonus questions at the end.